Okay, so with that we are coming to our next session. I'm jumping in for Dr. Uta Ceglarek, who couldn't attend this particular session. She will join us later. And the title of this session is LCMS Applications in Endocrinology, Improving the Diagnosis and Treatment of Endocrine Diseases. And the first speaker is Dr. Constantine Stratakis. He is professor of pediatrics at the University of Athens.
Good morning. I want to thank the organizers for the opportunity to present today here at this meeting. I'm a pediatrician, I'm a clinician, I'm an endocrinologist, I'm also a geneticist, and my lab is actually in Crete, although I was just elected to be here in Athens. The work I'm going to be presenting today is work that I did mostly in the United States. Some of the samples, specimens, have been collected here in Greece, because for many years I was at the National Institutes of Health at the NIH, where I'm still a investigator emeritus. So I will talk to you from the clinician's research endocrinologist perspective on the uses of mass spec in endocrinology. So this is a statement that I took from the internet. LCMS is the most widely used technology in various analyses due to its ability to separate and detect a diverse range of molecules with unparalleled sensitivity. And very clearly, this is definitely true. And what I will show you is 4 examples where my lab in our patients used LCMS to identify either new diagnostic molecules or see another aspect of an already existing diagnosis and obviously expand the hormonal spectrum of this diagnosis. So the first example, and the one I will dedicate most of my talk on, is the etiology of PCOS due to adrenal hyperplasia. And so this is work that we published back in 2021, but we are continuing this investigation. I'll show you the work we're doing right now based on this analysis that started in 2021. This is the first publication, so you can refer to the clinical data there. We obviously I don't know how many clinicians are in this audience, just wanted to remind you what polycystic ovarian syndrome is. The NIH criteria and the Rotterdam criteria basically focus on the presence of high androgen levels and menstrual irregularity in women. It's estimated to affect anywhere between 20 and 30% of women of reproductive age. I'm interested in the younger ages because as a geneticist as well, I want to see what genetic factors may affect this condition, which affects so many of our women. And in this study, we selected young girls starting at the age of 16. All of them had their menses around the age of 12, so they already had at least 2-3 years of menstrual history. And all of them were diagnosed with meeting this criteria with the polycystic ovarian syndrome. None of the girls was on OCPs, oral contraceptives, for at least 1 month before the study, and as I said, already had at least 2-3 years of menstrual history. We did not include in this population of young girls and women, we did not include any that had known diseases. And obviously we screened them, but we very clearly, these are, for all practical purposes, healthy otherwise, on no medication, right? So this is very important. You can see here that they met the criteria. Their testosterone levels were significantly elevated, as you can see, and the androstenedione were high, and the Matsuda index was high. So they were, they had insulin resistance, not very high, not like the older women with PCOS, but they had insulin resistance and clearly hyperandrogenic. So here, what we did was a test that we usually do for women or for men and women that have adrenal hyperplasia. And so what we did was we gave them dexamethasone to suppress the adrenal function, and then we measured steroids for 6 days, 2 days before the administration of dexamethasone and 4 days during the administration of dexamethasone. The clinical study was published in a paper that we published back in 2016. So we took the samples in 2016, we analyzed them in 2021, and we continue this work to this day. This is the results of the Little's test. That's what the test of the dexamethasone administration is called. And you can see that women, these young women with PCOS, all had higher urinary fructose, although not statistically significant, not very significant, but clearly higher, and higher 17-ketosteroids. Those of you that are not endocrinologists, these are the metabolites of androgens. Now, when we saw that, we also imaged the women that had the higher steroids, and very clearly, the women with PCOS had a slightly different size adrenals. And so this is obviously an objective thing. We try to do it with computed tomography measurements that look at the entire volume of the adrenal. And what we found out was that the volume of the adrenal was unexpectedly actually smaller rather than bigger. And we found that there was an inverse relationship between the amount of steroids excreted by these young girls and women, inverse relationship with the volume of the adrenal. And so what we did then, we suspected that something was going on in our population, because not everybody that we studied had smaller adrenals. And so what we did was we looked at those that had the higher amounts of androgens secreted, and so those we call high responders. And when we did that, there was a perfect correlation between the size and the high response. So smaller volume adrenal had a higher response of androgen secretion in response to dexamethasone. And so we looked at all the numbers that we had in our protocol and see whether there were indeed differences between the high responders and the normal responders. And there were differences. The high responders had more insulin resistance. And so not only they had higher androgens, and that was the selection, because they were higher responders, but they also had more insulin resistance. So we took these young girls and women and collaborated with Amanda Schwartz. I'm sure that whoever works in the mass spec of steroids knows Amanda at Stellenbosch University in South Africa. And we tried to look and see what are the steroids that are secreted by the adrenals in these high responders, women, young women and girls with PCOS. And these are some of the probes we looked at to try to differentiate between the various types of androgens. You can see here those that we found elevated, plus an unknown to this day. This is the ongoing work, steroid-eluting at 320 that is there. And you can see among the steroids that I just showed you, which ones were the most significantly elevated in the high responders, all identified by LCMS. This work has never been done in PCOS before. 16-hydroxyprogesterone was the highest, and progesterone also itself. And you can see some of the other steroids which also were elevated, and then the unknown steroid right here, which we're still trying to identify which one it is. The high responders also had higher cortisone and cortisol, not unexpectedly. Now, the significance of the identification of the 16-alpha-progesterone by LCMS in PCOS is very significant. It binds to the progesterone beta receptor. It has an unclear role in reproductive function, but it is an androgen. It's a weak androgen, but it is an androgen nevertheless. And so in this study, LCMS helped us identify a subgroup of patients with polycystic ovarian syndrome that mimic micronodular. So remember, the volume of the adrenal was smaller. Micronodular adrenal disease. It does not seem to be heavily related to insulin resistance, although by definition these patients have some insulin resistance. We do think that this obviously leads to altered reproductive function, and we identified 16-alpha-progesterone as the most significant weak androgen produced by these patients. Most likely, this is produced by the backdoor pathway in the adrenal. I don't have time to show you the backdoor pathway. And as I said, we are still working on identifying this other steroid that seems to be there, and this is work that's ongoing with Amanda. So this is story number one. And you can see from the physician researcher's perspective how LCMS was essential in helping us identifying a new phenotype, essentially, within the much larger group of women with PCOS. We think that this phenotype is probably about 10% or so of all the women with PCOS. The second story is this one. We published this paper 3-4 years ago, and again, this is work that's ongoing because we are continuing to, this is a multi-center study done at the NIH, started at the NIH, now it's ongoing in France and Germany, and with some samples from myself from here. So this is a mass spec-based steroid profiling in another disease of the adrenal called macronodular adrenal hyperplasia. In this disease, we have different types of nodules in the adrenal. You can see here the larger nodules and then some other ones that are smaller. Each one of these subtypes, and I'm not going to tire you with the molecular genetics of the disease, but each one of the subtypes my lab has found a gene for. So over the last 30 years, this is one of the major projects in my lab. We have found now about 85% of the patients with these diseases have a germline mutation in one or another gene. We have a total of about 5 genes now. And so in this study, we used LCMS to try to see whether the gene that causes this type of tumors has any particular effect in the steroid production. Does it actually determine a cell type, or if it is not the cell itself, a steroidogenic phenotype of the existing cells? Is that determined genetically? There's no question these patients get tumors, and there's no question these tumors all produce cortisol. But every clinician that sees these patients with Cushing syndrome knows that their Cushing syndrome is not exactly the same from patient to patient. And so the question is, since they have different genetics, and they have a different steroid profile, even the simple steroid profile, measuring cortisol or 17-hydroxysteroids, can you see by LCMS different steroids? And the answer is, and this would not have been possible to be answered without LCMS. The answer is yes. As you can see here, now, I don't want to tire you again with all the data, but this is a macronodular adrenal hyperplasia negative for this mutation, and macronodular hyperplasia positive for this mutation. The gene is called ARMC5. It's one of the genes we have found. And so you can see that there's a completely different hormonal profile in the ARMC5 positive macronodular hyperplasia leading to Cushing syndrome versus the macronodular hyperplasia due to leading to Cushing syndrome that doesn't have ARMC5 mutations. And these are statistically significant differences. And we identified specific steroids. Again, I don't want to tire you with the results, but there's no question that you can use LCMS to identify the steroid phenotype. And again, these are, for us, for endocrinologists, for researchers in this field, LCMS is still out of use, of everyday clinical use. And so what I'm pointing out here is that whether it's going to be in the next 5 years or the next 10 years, there's no question in my mind that we will be using LCMS to identify the molecular subtype because of this knowledge, right? So because you know that the steroid will be different. Then the third story is actually even more significant, I think, clinically. One of the problems we have in endocrinology is to identify who has proper adrenal reserves, who has adrenal insufficiency, who doesn't have adrenal insufficiency. These are not insignificant diseases. 0.6% of the population at some point in their life are diagnosed with adrenal insufficiency, inadequate cortisol. And 6.6% of the population can have hyperfunction of the adrenal. That includes the average 50-year-old with metabolic syndrome. And so the question is, can we use LCMS to identify better who is at risk for adrenal insufficiency and who is better diagnosed with cortisol excess among these patients? This is a study that was done by my good friend Solden at the NIH, Solden is now retired. He came to the NIH from South Africa. And so he showed that by LCMS, if one measures aldosterone during ACTH stimulation, or even better, DHEA and 11-DOC, you can identify better the patients that have adrenal insufficiency. The differences are significant. This is a measurement of 11-DOC in response to ACTH compared to the response of cortisol. And this is, again, 11-deoxycortisol. And even 11-deoxycortisol is better at the ACTH than cortisol. Again, this you can't measure accurately with routine assays. This is all detection by LCMS. And so in this table that Solden has published now, you can see how the criteria change using, instead of using simple cortisol, using 11-DOC and or aldosterone. In this case, I show you the 11-DOC. Most recently, Solden's assay has been used to identify something that, again, by routine assays we did not know about. For example, I don't think it was widely known that dehydroepiandrosterone has a very significant diurnal variation, which you can see here. So when patients get sent from the doctors to the lab to measure DHEA for assistance in diagnosing adrenocortical insufficiency or for diagnosing an adrenocortical tumor in case of adrenal excess, it makes difference what time you send them to the lab. Look at the 8 a.m. DHEA levels and the midnight DHEA levels. Now, if you try to do this with routine assay, you'll see no difference. But the DHEA levels by LCMS show a clear diurnal variation. We extended the study, and these are all data from NIH, that this particular table hasn't been published. And so we extended the study to a number of other steroids. And you can see that by LCMS, I think testosterone was known that it has a diurnal variation, even from the routine assays. But most of the other steroids here were not known. Cortisol does, of course. But 11-DOC, androstenedione, and DHEA were not known to have such a significant diurnal variation. It was only through LCMS. And then the final study, many of us are using statins. And at the NIH, we did this study just a couple of years ago, and we used samples collected from patients that were getting statin for a different protocol. And I don't know how many of you realize that statins can actually affect steroidogenesis. The problem is that when we first measured steroids by the routine assays, whether it was HPLC or even worse, radium assays, we saw absolutely no difference. It was only LCMS that allowed us to see that, in fact, acute statin administration clearly reduces steroid production by the adrenal. Now, the good news is, if you were asking, if you are taking statins, the question, are you adrenal insufficient? No, because ACTH rises, and so it compensates. And so I'm very careful here to say that it is only the acute statin administration. Now, of course, if you take statins chronically and statins decrease cortisol production, then ACTH rises, and yes, you're fine with cortisol numbers, but that means you also get a little bit of adrenal hyperplasia with whatever that means for your overall health. And that's something that's not being discussed, of course, by clinicians that give statins. And this is the data using LCMS for baseline, this is cholesterol, androstenedione very clearly, corticosterone, cortisol. You can see the decrease in cortisol values after the acute administration of statin. DHEA didn't seem to be affected much, but very clearly 11-deoxycortisol was also significantly decreased, and corticosterone, this is not statistically significant. This was statistically significant, and this was statistically significant. So, I changed a little bit the statement from the internet here to fit my talk. Liquid chromatography mass spectrometry is an amazing technology for endocrinology due to its ability to separate and detect a diverse range of molecules with unparalleled sensitivity. It was used successfully in our case in identifying the etiology of PCOS due to adrenal hyperplasia. There's approximately 10% of the patients that have this particular phenotype of PCOS. It allowed us to diagnose more accurately the steroid secretion and the particular steroidogenic phenotype of patients with Cushing's syndrome that have various types of nodular adrenocortical hyperplasia. Then it was essential to show us that you can use other molecules to make the ACTH testing for the diagnosis of adrenal insufficiency more accurate, and it detected diurnal rhythmicity in steroid secretion, something that's not often appreciated by clinicians. Finally, I showed you the small data for the detection of steroid hormone changes when using statins acutely, when you first administer statins to a patient. So thank you very much for the opportunity to present. Obviously, this is my team at the NIH. I'm now at ITA in Heraklion. This is my lab at ITA. We do mostly genetics right now, but obviously we participate in all the studies I showed you, which are right now done internationally. And this is my company here in Athens, Astra Health, and my email if you have questions. Thank you so much for the opportunity to present here today. There are questions?
Actually, thank you. I'm coming with a question. You mentioned that you detected, for example, the diurnal variation in hormones, or in DHEA. So, is this the fact that these are not visible with the traditional methods? Is it due to modifications? Do you have any idea why there is this discrepancy?
I think the biggest problem is the accuracy of these assays that exist right now, even HPLC for steroids, especially when the values are lower. We know, for example, DHEA, the assay is horrible. For other steroids, DHEAS is a better assay. So I actually, unless done by LCMS, I don't rely on DHEA by routine labs. Estradiol and testosterone at low values by non-LCMS methods are useless. And so I think it has to do, with the technology and the steroid. Not all steroids done by HPLC or even radioimmunoassay are useless, but some are. And the point is that the clinicians need to know this. When I was deputy editor of JCNM, we actually wrote an editorial. This was my term ended in 2015, and I supported an editorial to say that in the United States, no lab determines low testosterone values and estradiol values for clinical use unless done by a validated LCMS assay. We had to withdraw the editorial for financial reasons because so many people wrote against this policy. It's amazing to me. This happened in 2015. That's when I was deputy editor. It's amazing to me that today, in 2024, there's still no uniform policy to not accept estradiol and testosterone values, and I would add DHEA values and delta-4 estradiol, when especially at the low ends of the ranges, from non-LCMS methods. It's horrible. When I review papers and I see studies using testosterone, estradiol, DHEA, delta-4 estradiol by non-LCMS, I say to the editor, it's rejectable, just simply because of that. I really don't care about anything else about the study. But I guess because LCMS hasn't penetrated everywhere, it's still being used.
Okay. Thank you.
Thanks.
Hi, in your PCOS cohort, was there any effect of BMI on the results?
So this is a very good question. The question was whether these patients had different BMIs. These young women and girls were not very obese. I think I had the BMI on the clinical description. So this is a very specific, it's a very particular phenotype, these patients. They tend to be leaner, they have less insulin resistance, but they tend to have more androgens. And they end up having clearly the same effect on the ovarian function, so they have irregular menses and they have inability to conceive, but they're not the insulin-resistant phenotype. They are the androgen excess phenotype. So it's within that group of clearly androgenic excess. Now the question is, and I don't have the answer to that, if you follow these women, when they're 30 or 40, or after they have their first pregnancy, will they still be lean? I don't have the answer to that. If I were to guess, I would guess no, because they do have some insulin resistance. And so whether they retain their leanness long term, it remains a question. But thank you for the question, yeah.
Okay, thank you. Any other questions? Any questions online? Okay.
Thank you.
Thank you. Okay, our next speaker is Dr. Alexander Gaudel from ILM Leipzig in Germany.
Hello, everybody. I can already see that this is a little bit messed up, but let's hope that this is not going to happen further in the talk. So in the beginning, it's great that I can immediately pick up on adrenal hyperplasia from the talk before, and I will bring it in a little bit different direction. As you can see, it's going to be about a congenital form of the adrenal hyperplasia, and I will take a very short time in the beginning to bring everybody on the same page when it comes to CAH. So which button? The big green one, apparently. Yes. Okay, so now just very quickly, what is CAH? It's a congenital dysfunctional steroid metabolism. There is the the enzyme, the 21 hydroxylase, which is deficient in this case. This poses a roadblock in this metabolic pathway, and the corticoids are not being synthesized or are not sufficiently being synthesized. This generates a feedback mechanism towards the hypothalamus and the pituitary, leading to more ACTH, increasing the adrenal activity, and in the end, generating the adrenal hyperplasia. What it does not do is produce corticoids. In fact, or instead, it produces more of the precursors, which then leads to an increased concentration of androgens, which then result in virilization and hyperandrogenism. And we can see that this is, again, a little bit messed up here. But OK, it doesn't matter. This, however, is not the critical, or not the concern in this illness. The critical part is the lack of corticoids, particularly the aldosterone, for example. This can lead to a salt wasting crisis, which can be life-threatening for a child. And this is also why it's very important, or let me rephrase that. When we detect this very early in the early living days of a child, we can very easily manage this into therapy as a treat this. And that's why it has been implemented in newborn screening like decades ago. And I'm going to talk about newborn screening in Germany now a little bit, because there we have a law. It's called the Kinderrichtlinie, the like children guideline. And in this law, it is stated how this disease is supposed to be measured when it comes to the methodology. And unfortunately, a law says, here this is the German abbreviation, AGS for CAH, it says that it needs to be an immunoassay. And this has been like this for decades. And yes, we know immunoassays are still great, and they're highly developed and automated and everything. It's all great. They have their flaws when it comes to specificity. We already have heard about this, a couple of examples today. So this lack of specificity decreases the quality of the NBS, the newborn screening in general. And what's a good measure for the quality? It's the recall rate. In Germany, we have a yearly screening report, and when we go back 20 years, we see here the recall rate published in the screening report was an average of 0.3%, which is not great. It has been historically for the CAH newborn screening always been on the higher side. And 10 years later, we see it's still the same number and nothing has changed at all. Except one thing has changed in 2 labs. They implemented a second-tier LCMS method for the confirmation analysis of these positive samples. And as you can see, they managed to get the recall rate down to 0.02%, which is great. And then we fast forward a couple of years more, we see that the values they did not change, but the number of labs implementing second-tier analysis has increased, which is great. But now the question is, how does LCMS do this? And as everybody knows, of course, it comes down to the quantification of the 17-hydroxyprogesterone, which is the key parameter for the early diagnosis of this illness. Now, this concentration is dependent on a couple of factors. For example, on biological factors, on the birth. Are there aggravating birth conditions? Is there perinatal stress? Is the children being born sick, for example? Or as another example, there are certain enzymes associated to the steroid metabolism that are not yet matured in a preterm born baby. On the other hand, there's analytical factors like specificity of the method, or also pre-analytical factors like contaminants, which also pose a very big problem for immunoassays, reducing their specificity. And due to this reduced specificity or low specificity, results often come out, often as not correct. from time to time, results come out false positive. And this is something that we don't like, and we want to decrease that. And LCMS, as we heard a lot today, has the power to decrease this. I won't go into any details here. Luckily, we had the introductory talk this morning. But what it does, what enables, is a multiparametric analysis of several analytes simultaneously, so that we can then do calculate ratios like these. And with these ratios, we generate a certain discriminatory power that is very, very good at discriminating between healthy and sick children. Now, why are we not using this in the newborn screening for CAH? And the reason there, it's too slow. It takes time. These LCMS methods, when they're fast, they're 5 minutes. And a lot of them are even slower. The commercial ones are way slower, so we cannot use them. But unfortunately, fortunately, we can control a couple of things. We see here a chromatogram of our serum steroid routine method that we use in Leipzig at the ILM. And the time that we need to reduce essentially is the run time. We can control this very easily through the LC parameters, of course. That's not a problem. But if we do so, we basically shove everything together and reduce selectivity of the method. Also something that we do not like. However, this is maybe just another problem to be solved. So, reducing the run times, check. How do we increase the selectivity now? You might have guessed it. We're going to use the mass spectrometer for that, and it's quite easy here as well. No, quite easy is also a little bit of an oversimplification. How do we increase the selectivity? We leave the realm of the regular SRM, MRM experiments that we use for basically most or nearly all of our experiments, and we dive one dimension deeper into MS cube or MRM cube. This basically introduces, or it uses an ion trap that is installed in the third quadrupole in Q-trap systems, not in all triple quads, only Q-trap systems have these. And we can use this to form or to take a product from the collision cell, collect it in the trap, and fragment it a second time, so that we have a precursor product, first generation, product second generation mass transition, a two-stage mass transition. This adds an insane new amount of selectivity or specificity in this case to the method, and really helps in mitigating interferences or mitigating the effect of matrix or whatnot, other components, constituents. So here you see a chromatogram of the method that we composed like this and with a couple of parameters, and you see we have our 17-hydroxy, 17-OHP peak here at 0.9 minutes. The method, or the run is 1.5 minutes long. And with this method, we set out and to try to not to produce another second-tier confirmation assay. No, the idea was to better attack the primary screening, to show to give a replacement, a potential replacement for primary screening. Okay, so we increase selectivity. Just to round out the sample prep, very quick, this methanolic extraction basically, nothing to write home about. We can do this on a 96 well plate or in Appes, Eppendorf vessels, very straightforward. Okay, so now some data. At first thing to be talked about, we're using the Autodelphia neonatal 17-OHP kit, which is an immunoassay calibration control kit. That's weird, yes, but it works. It actually works, but only with this screening, MS3 screening method that we're using. In fact, when we measured these calibration and QC material with our regular method, with a longer chromatography, we had interferences like hell, and we couldn't reliably quantify anything. The application of the MS3 detection eliminated all of the interference, and we, since then, we successfully participated in ring trials by RFB, and then got very good values there. As you can see, the CV, the imprecision of the method, is a bit lower than you would expect from an LC-MS method, and in fact it's also lower than the Autodelphia automaton I have here put here for comparison. But still, on the one hand, the accuracy is similarly great, and also these values fall very comfortably below or within the values given in the Riliebeck, which is a guideline from the German Association of Medical Quality Assurance for lab experiments. Okay, we do want to apply this method to a clinical cause, so we need to validate this clinically. For that, we did a study, big study. We took basically all of the positive newborn screen samples for CAH that we had, was 738, and we supplemented them by a couple of negatives to round a little bit out, try to distribute across maturity groups as far as possible, and we made 4 maturity groups according to WHO guidelines. On the one hand, using gestational age, and on the other hand, using birth weight. So that's the 2 possible ways that we got. We have these 4 groups, and going from basically, so with decreasing maturity from 1 to 4, all of these samples were measured by LC-MS3, and for the cutoff calculation, we then designated the 99.5th quantile within each group. We excluded a couple of samples for obvious reasons like confirmed CAH cases and stuff. And the cutoffs that we got from this, what we're going to talk about next. And as you can see here, there's now different information to be gained from. The first information, so we have the 4 groups and always the 2 strategies. As you can see, with decreasing maturity, we have increasing cutoffs. No surprise, this is what we have known for many, many years, and also the immunoassays, they have age-dependent cutoffs, so this fact is still valid. Obviously, biological variance is also a thing when you measure with LC-MS. The next thing that we see is that the cutoffs themselves, they are quite similar, independent of the strategy used to calculate them. So it doesn't matter if it's weight or age, the cutoffs are quite similar, as are the interquartile ranges down here. As you can see, they're quite overlapping. So these were basically the 2 takeaways from this slide. Now the next thing is how do these cutoffs actually fare in the entirety of the study cohort? We're comparing these with the immunoassay values that we had, like from our primary screening. So we have, and please, I'm always hitting the wrong button. This is quite anticlimactic now. Please mind the logarithmic scale down here, so it's 730 samples. We see the true positives, the 7 true positives that the immunoassay got, the false positives, the 730, and then the rest are the true negatives. Now, the 7 true positives, they were all being found independent of what strategy or method. So this is very important, and that's great. And as you can see now, this bar has shrunken massively from 730 false positives to roughly 30. The one is 31, the other one 28, I think. So this is already an insane decrease in false positives. The thing is about these false positive samples, they're not identical. So if we combine both strategies, so the weight and the age strategy, we can even reduce the number of false positives more. We can basically halve it. So we're left with 15 false positive samples from the initial 730. The positive predictive value, I did not mention before that, increased from 1 to 32%, and is also a very, very significant increase, obviously. How do we now project these onto like reality and a sample cohort that's actually resembling what the regular population? Oh yeah, that's right. Brought something new in. I want to have a closer look at the false positive samples and to figure out why it's so cool to combine the gestational age and the birth weight. Disregard the coloring of these circles. I messed that up myself, so just go with me. When we have a look, so here, cutoff, we have 31 false positives here, 21 here, 28, sorry. And if we now only look at the term-born babies, we have like 11 false positives with the age cutoffs and 3 with the weight cutoffs. So weight seems to be working better here for the term babies compared to age. For the preterm babies, it's the other way around. And if we now have a look at the weight, the regular weight-born babies, with 9 for the age cutoffs and 14 for the weight cutoffs, seem to be working better with the age cutoffs. And again, for the low-weight children, it's the other way around. So what we could basically derive from that is that the weakness of the one strategy is being balanced by the strength of the other, making it like a no-brainer to combine both of them, which leaves us with these remaining 15 false positive samples. The entirety of the remaining positive samples, back then I was wondering, might there be still a system to the occurrence of these samples? And that's why I plotted them like this. I'm sorry about having red and green in the same picture. I do not do this anymore, and I urge everybody to not do this. But you can focus on the black dots, basically. It's because there's 15 black dots here. It doesn't matter whether it's the gestational age plot or the birth weights plot. And as you can see, there is no real pattern to be seen here. So there's no new information. So it seems to be rather random how they occur, these false positive samples.6However, all of these samples had one thing in common, and that was stress. There were sick children, there were multiple births, they were CAH cases, obviously, with the purple circle around. They all had, at some point, aggravated birth conditions, and that's the common denominator here. And this is something to keep in mind. Now I want to try to project this onto a real cohort, and we start with our immunoassay, the primary screening that we actually do. So we have these 738 positive samples as a subpopulation of our study cohort, which gives a diagnostic specificity of these 58%. And during the proper time period of the study, where we had short of 95,000 samples, and projected onto all these, we have a specificity of 99.2%, which is still quite bad, actually, for newborn screening. And now we take all these and run them through our mechanics, through the margins. We get our 15 false positives, these 7 true positives, leading up to a 99.1 specificity within the study cohort. And now there's a point where I have to make an assertion, and the assertion is that all true negatives from the primary screening using immunoassay stay true negatives if they were to be measured using LC-MS3. In my opinion, this is not an unreasonable and actually quite a reasonable assertion, but still it's an assertion. So if we do this and calculate the specificity for the entire cohort again, we come up with 99.98% diagnostic specificity. And here, a short throwback to the beginning of my talk, where I showed you the recall rate of second-tier methods, and this is basically the same. It's basically the exact same range that could be reached without second tier. Now, as it says in the title, it's kind of fake. And it's kind of fake because I assert it a lot. And this brings me to my limitations. And it's mainly and foremost the size and the composition of the sample set. The groups are not evenly distributed. We have very few cases, so this is something that needs to be improved upon. Also, as I said, the specificity is only true for the combination of the immunoassay and the LC-MS because we obviously could not measure 95,000 samples using our LC-MS method in the time. But now again, to end my talk, I want to show you some real numbers from the past year. And in June 2023, we implemented these cutoff values, and since then, we got 189 samples from the primary screening as positives, measured them using LC-MS3, and when we do our thing, we end up with 13 samples left, 13 positive samples. 7 of these were actually diseased children, sick children, one of them even a confirmed case of CAH. Unfortunately, 6 of them were healthy. That's not great. So in any case, what this leaves us with is the necessity of second-tier analysis. And with this, I want to conclude and give you kind of an outlook with an image. So imagine in a world where we have access to second-tier multiparametric calibration and control material, which is today. Not when we did the study, but it is today. With this calibration and control material, you do your LC-MS screening on this very instrument, and then you get a flagged sample, a positive sample. And the only thing you have to do then is go to your MS operating PC, hit a couple of buttons, and immediately re-inject the exact same sample from the screening, from the same plate or whatnot, just by using another method, a multiparametric method. So you have the screening and the confirmation from the same sample preparation, on the same instrument, on the same day, within very, very short time. So let that sink in. I think it's a cool image. And with that, I'd like to end my talk. Thank my institute and all people involved in this endeavor. Of course, Professor Ceglarek, who apparently is not here, unfortunately. And I would very much like to thank the IFCC for inviting me here. It's a great honor and great pleasure. And when I read the preliminary program and I saw all the names, and I was like, what? and me too, that's cool. So thank you very much, and thank you for your attention.
Thank you for this very nice presentation. Any questions?
That was a great talk, really interesting.
Thank you.
Now, I'm a little bit confused by all of this. I've never done newborn screening, but I was involved with a small study looking at neonates a few years ago, and we did look at some steroids, including 17-OHP, in serum, plasma, and whole blood. And we seemed to find a 30% difference between the whole blood and the plasma levels, which implied that there was some kind of protein binding going on, and could you really, and this could possibly be PCV related. Now, is there a difference between patient samples if the PCV is different?
What is the abbreviation that you used?
Pardon?
The abbreviation that you used in the end, it was acoustically, so you want to compare the whole blood and the plasma values, or what do you mean?
Yeah.
It's basically, so there's a correction factor for hematocrit, for example.
Yeah. So would you not see that, A, on the spreading on the paper, because the different hematocrit's going to give you different spreading, so you're going to take up a different volume. Mm-hmm. And then also, if you've got different hematocrit values, are you not going to be seeing differences in the total concentration?
So this is basically normalized entirely, and since the calibration material and QC and everything is entirely the same, we're not comparing this with serum values.
Right.
Or maybe I'm not getting your point correctly, because it's hard acoustically to hear you, actually.
Yeah, sorry. Yeah, perhaps have a chat later. Yeah.
Pardon?
Perhaps discuss it later.
Yes, I would very much like to, yes.
Okay. Any other question? None. I just have a quick question about, MS3. Sometimes there are some sensitivity issues when you go to level 3 with mass spec. What are your experiences with that?
Yeah, that's the thing. I forgot to tell that, actually. So, as I told you, this MS3 eliminates interferences like magic. But magic always comes at a price. And in this case, the price is, in fact, sensitivity, it is precision, and it is time. And this is a rather big disadvantage. So because, sensitivity-wise, we lose, I don't know, don't want to come up with some random number, but we lose a little bit. And precision you have seen, 10 to 13% CV. The time is the more striking thing, because, so I'm talking about cycle time, MS experiment cycle time, and using MS3 is so slow that I would never recommend using more than 2 mass transitions within a given method. So for example, in this case, analyte and internal standard, and that's it. It depends, of course, on your chromatographic separation, the width of your peak, and the number of data points that you want to have. But this is the biggest restraint for this kind of technology. The sensitivity issue is, for this application, it's not that bad. The sensitivity is way worse than the immunoassay, for example, and the LOQ of this method is 5 nanomole per liter, while our serum LOQ, for example, is 0.2 nanomoles per liter. But the intended use is different. 5 nanomole per liter is way below the lowest decision point already. So we don't need the insane sensitivity. We could increase the sensitivity with more time that we put into the MS experiment, meaning there is a parameter called fill time. It just basically says how much time does the trap use to fill itself with ions. And we could do this very, very long, but this makes funny effects on the peak shapes, and it's not great on precision. So MS3 is, so when we say MS already is complicated, MS3 is way more complicated than that, yeah. But the application is not.
Thank you. Well, if there are no other questions, then we can conclude the session. Thank you.
Thank you very much.
And